to start transforming our interpreter in this way, we've actually already taken the first step, which is to convert x per c's to x per d's. And the point of this conversion is it eliminates runtime names like x. We don't have to deal with x at a machine code or assembly code level. So if we look at our interpreter after we have this compiler, we have x per c's and x per d's. We're not going to worry about the parse function when we think about supporting machine code because we can always parse and compile our programs in advance. So parse and compile are not what we're looking at. You can imagine either compiling in advance or after you have your curly brace language working in machine code, implementing those pieces in the curly brace language. So we're interested in interp, and this is where we've started making progress, where we don't have names anymore, we just have listref, which is something closer to a machine operation. So that was step one, but now we're still relying on quite a lot of racket or PLAI typed here. We're still relying on type case. We are relying on recursive calls and implicit continuations when we call interp here. Now, in terms of those implicit calls or implicit continuations, we know how to deal with that. That is, we will take our interp and split it into interp and continue, where we make the continuations explicit. Of course, a machine often does provide a notion of a stack, which is where recursive calls can happen, but as we saw with continuations, that stack model doesn't match up exactly with what we want for the book language, where something like this interp for a function call, that's a recursive call, but it's in tail position, and so it shouldn't use up continuation space, it shouldn't use up the stack. So that's why we're going to ignore the stack and make the continuations explicit. So that brings us to version 2 here, where we have the same x per d's, but now we have continuation records with the usual done k, add second k, and so on. So that gives us interp and continue, like we used to have. To interp a plus d expression, you start interpreting the left and extend the continuation to say add second k, and meanwhile continue has an add second k case, which will start interpreting the right, and so on. So that takes us another step towards an interp and continue now that can be translated to machine code. But we're still relying on many things. Even still, we're relying on function calls. Now we know these are tail calls, so they're not extending any implicit continuation, but it's still a larger concept than you would normally get out of machine code, which gives you just a goto and gives you registers for storing arguments, say. So our next step is to take our function calls and translate them to something that looks like using a small number of global registers and a goto. So we're going to take a call like interp env add second k, and we're going to change that so that we go to interp just by calling it with 0 arguments. Right? And this is a fine approximation of machine code in racket because we know that a racket call, a tail call with no arguments, is just like a goto. Right? In any case, you'll be able to convert this to a goto at the end. Meanwhile, to pass the arguments l, env, and add second, we'll set registers. So x per reg is going to be a global variable, and here we're changing that register to have the left expression, and we're changing the k register, the continuation register, to have the add second. We don't have to set the environment record, which is an argument for interp in this case, because it just stays the same as it was. So when we do that, we get interp and continue that look like this. Here's interp, and where we start interpreting a plus expression, then we set the expression register to L, right, which is the left expression, and we're going to jump back to interp. Meanwhile, we've extended the continuation register, extended the continuation. Here we took the old value of the register and put a new value that's an extension of it. Of course, this is a high-level operation, but we'll get to that in a minute. So here I've got a couple of registers, x per register and env record. Both interp and continue can share the k register for the continuation. And you can see that continue also takes no arguments, and it does a type case on that continuation register. When add second k wants to start interpreting the right expression, it sets the expression register to that. It sets the environment record to the one remembered in the continuation. It builds a new continuation for the k register and jumps to interp. So all the cases of interp and continue end with either a jump to continue or a jump to interp. So that's a step forward. We've made all argument passing explicit. We're not relying on functions at all in the racket level. Not only we're not relying on continuations, we're not relying on argument passing. We're just using registers and gotos. But of course, you still see this thing that looks like a function call here, add second k, and that's really an allocation of a record.